described here. So the procedure is obviously always the same, yeah, how to determine the winner and the loser stock. So it's actually quite simple to do this in a matrix program such as MATLAB or R. Obviously, you write the code once and you can make small changes, and then you get basically always a different sort of strategy. Yeah. So in this case here, this strategy is called the so-called 6-1-1 strategy. Yeah, where we always skip 1 month. Yeah, obviously here in between the when we form the portfolio. Yeah, the most recent months here, this period here is always skipped. Yeah, we do not take them into account. So we start after that with cumulating the returns. Why is that, you may ask? So the answer is that in stock markets, yeah, in the 1919 paper, Jägerdesch found or documented the so-called short-term reversal effect. So which means that that stocks that have performed very poorly in the previous months, yeah, here, they tend to outperform in the next period, whereas stocks that perform very well in the most recent past month, they tend to perform poorly in the holding period. Yeah? So which suggests a sort of negative autocorrelation. Yeah? So the short-term reversal effect corresponds to negative autocorrelation, right? But this momentum effect, it's the opposite. So it predicts positive autocorrelation because it says that past winners outperform past losers. So because we don't want that our momentum effect is, let's say, polluted, yeah, polluted from this short-term reversal effect, we try to get rid of it from the implementation of our strategy, and that's why we just skip these most recent past months. So let's just take this away here. So, as I said, that is the so-called 6-1-1 strategy, yeah, where you cumulate the returns until months t-6, yeah, and the standard momentum strategy. This is basically the strategy that is discussed in the paper from Jägerdesch and Tiedemann, but they discuss, of course, also other strategies. Yeah, but this is sort of the main strategy, yeah, the key of the paper, the core of the paper. They use this strategy to report their result. And if you consult the Farmer and French paper or the momentum papers from Daniel and Moskowitz, you will find that they use another strategy, yeah, where they accumulate the returns from the t-1 until t-12 instead. Yeah? So they take a much larger accumulation period of cumulative returns. Okay, so here they basically this is then referred to as so-called 12-1-1 strategy. Yeah? Yeah. So you start to accumulate the returns at time t-12. You accumulate them until here. You skip 1 month. 1 month is a skipping period, and this denotes the holding period, yeah? Which is 1 month. So, and papers also use other holding periods, but in most papers they use a 1 month holding period return. Yeah? So the first figure again denotes where we start. The second figure denotes until when we cumulate. Yeah? So not until time t is 0, but we stop already 1 month before. Now we skip the most recent months in our accumulation, in the calculation of the cumulative returns, and we hold it. The last figure denotes the holding period, which is 1 month. Okay, so that's the 12-1-1 strategy. Yeah, the principle is exactly the same. Yeah, for all our n stocks, we do the same thing. Yeah, we accumulate the returns. We compound the cumulative returns within this time period here. Yeah, we store them in a vector. If we sort the vector, then again we determine where to find the 10% of the loser stocks, where to find the 10% of the winner stocks, what's the threshold. Yeah? In order to do that, we need to know where's the threshold, what's the threshold. Then we code where they are located in our data matrix, and then we can compound the holding period returns. Yeah? And obviously, if we have a data matrix that has a dimension of capital T, and we have a accumulation period of let's say K, yeah? So obviously, if we implement this strategy here and we have capital T time periods, we lose K observations. So our forecast period or holding period obviously has then the dimension capital T minus K. Yeah, that's also important to know. So then there's another momentum strategy that has been proposed from Novimarx. So Novimarx argues that the actual information of the momentum effect is actually far away from today, and he suggests to accumulate the returns from T minus 12 until T minus 7, given today we add time T equal to 0. Yeah? So he skips basically the first 7 months in his in the implementation of his strategy when compounding the cumulative return. Yeah? So his strategy is then this 12-7-1 strategy. Yeah. So you compound the cumulative returns from T minus 12 until T minus 7, yeah, for these 2 months, and then you determine which of the stocks have the lowest and which of the stocks have the highest cumulative return given this time period. Yeah, you determine where to find those stocks, and you keep them. You keep the winners and losers 1 month ahead. You buy the winners, you short sell the losers, compound the holding period return, then you do the same thing again. Yeah, moving this time window 1 month forward. Yeah, that's the so-called 12-7-1 strategy. So and obviously there are many different strategies discussed, yeah, in the literature. And for those of you who took the RFM course, Research in Financial Markets, we also discussed that some some recent studies, they compound the so-called, they implement the volatility managed momentum strategy. Yeah, so they scale the zero cost portfolio, yeah, depending on the past volatility of that momentum portfolio. Yeah. But that's perhaps something that we do not address here in this course. So that's basically very easy to implement, yeah, and I will also show you later on in the code when we go to the coding part in MATLAB how we can easily just make some small changes in the heart of the code, basically, in order to get many different momentum strategies. Yeah, basically using the same code. Just have to make some very minor changes in the heart of the code. So these are the basics that we would like to go through, that you need to know in order to have the corresponding tools in your hand, so that you know what's going on, and that you can basically operate with the exercise sets that we will discuss for the MATLAB codes. Then we would like to discuss some simple basics, yeah, in MATLAB, some basics in MATLAB. So let us define, because obviously MATLAB and R, these are programs that are strong in linear algebra, and it's basically, you have already seen, you have already recognized that everything in econometrics is based upon matrix notation and matrix algebra. So very simple to use, obviously. Let us define a very general matrix A, with elements A11, A21, A31, A41. So we have here obviously dimension, a row dimension is 4. Then we have here next A21, A22, A23, A24. Then we have here A31, A32, A33, A34, and finally we have A41, A42, A43, and A44. Yeah, so what we have here is a 4 by 4 matrix. Yeah, very general 4 by 4 matrix. And this matrix, obviously, yeah, it has the same column and row rank. Yeah, it's 4 by 4. So if I define now in using MATLAB, I define a vector x. If I write this into the command window, x is equal with a double point 1 parenthesis closed. What it will give me, yeah. So the first item here denotes always the row. It's the row index, and the second number here denotes the column index. Yeah? Row index, column index. So if I define this vector here, it says, okay, give me in column number 1 all rows. Double point means give me all entries. So basically what it will give me is, it will give me this vector here. It is a column vector that consists of the element A11, A21, A31, A41. So x is then a 4 by 1 vector. So that has the dimension. So x is element m 4 by 1. Okay. So that's very important to know, because you should not confuse the column and the row index. So, and usually if you write this in the command window, MATLAB would spit you out immediately the entries here, these 4 entries. So if you don't want that, if you just want to store what you have defined here, you write a colon. Because then MATLAB does not spit it out immediately, but that just stores what you have defined here in the system. If you say, okay, no, I want to have x, or I can define x1 as a new vector. Let's say I define it as a, again, double point, comma, 2, double point 4, colon. So what does that mean? If you define this, it would give you a matrix, right? It says, okay, I want to have columns 2 to 4, which is this guy here, this guy, and this guy, and all rows. So give me all rows in column 2 to 4. So what it would give me, it would give me a new matrix. It defines this matrix here. This is what x1 would be. So x1 would be obviously a 4 by 3 matrix. So x1 would be element m 4 by 3. So that's a matrix. Next, if I define an x2, let's say x2, I define it as a 1, comma, double point. What's happening now? So obviously I say, okay, I want to define x2 as give me the first row of matrix A and all columns. Again, this is the column index here, and double point means I want all columns. And here we determine we want only the first row. So what it would give us here, obviously, it would give us this guy here in our matrix. So it would be then a 1 by 4 vector. Yeah? And again, if we don't want that MATLAB splits us out, immediately what it is, we write a colon. But we know that our x2 is a 1 by 4 vector, right? So what else can we do? Yeah, very simple. We can define W, rewrite zeros, parenthesis open, 3, 3, parenthesis closed. If we push then the enter button, MATLAB will spit us out this kind of matrix. It's a matrix consisting of zeros, yeah? And it has a dimension 3 by 3, 3 columns, 3 rows, or vice versa, 3 rows, 3 columns, yeah? Because we start always with the row index and then the column index. If you don't want that, you just want to store this matrix consisting of 0 entries, we just write a colon again, and it is stored in the system. We can also define y as we plug in, we write ones, parenthesis open, 10, comma, 1, parenthesis closed. What MATLAB now gives us is a vector that has 0 entries, that has ones, yeah, ones, and that has 10 rows and 1 column. So it's a column vector. Yeah?